Okay, welcome everybody to our CSP seminar this week. We always thank our sponsors, who I forget who that is this semester. So, you know, I don't know. Okay, it's our great pleasure to have Professor Liyue Shen giving today's seminar. She got her PhD from Stanford University, and then she did a postdoc at Harvard University, and now she's with us. Yay! And so everybody's looking forward to your presentation.
Thank you so much, Jeff. I really appreciate it. Yeah, so okay. Yeah, thank you so much for the kind of introduction, Jeff. Yeah, and I know some people here in the classroom. I also see some people in the lab, in my class. So very happy to see you here. And so as mentioned, I'm a new faculty, just joined ECE this semester. So there is some interesting things. So when I see like the emails about this semester, they list my title as an associate. I think, oh, totally, definitely cannot be. That's so early after 1 month officially joining. Yeah, so for today's talk, I will discuss some very, very recent works in my lab about the diffusion model and also about the latent diffusion model for solving inverse problem. And since I just joined here, and this is also my first talk at the CSP seminar, so I want to introduce something at the beginning very briefly about my general research work, what I'm doing, what my lab is doing, what I want to pursue in the future. So if you are interested, feel free to reach out to me. I'm very happy to work with more students here. And then we will get into the specific paper we discuss here. And more importantly, the two co-first author is also in the classroom for this paper. They will definitely know more details in the experiments than me. So I'm sure if you have any questions, they can answer any of that. Okay, cool, let's get started. So firstly, as we can see the improvement of the AI for the recent years, and not only in AI, and also the generative AI. For example, we can see like what's happening last year about the ChatGPT, which changed even almost everyday's daily life. And also the apply for like the AlphaGo for the self-driving. This is very exciting, as well as the as well as the field for the biomedicine and healthcare. Yeah, let me see if I can remove this. Okay, cool. So we have seen like back to the 2016 when people are firstly using the deep learning model, train the deep learning model on the large scale skin image for the classification task. We have also seen like how the AlphaFold has been so useful for predict the protein structure and also segmentation, patient healthcare. So all of these kind of exciting things are happening in the field interdisciplinary between the AI, machine learning, and also biomedicine and healthcare. So this come to my field, which is I call the biomedical AI, which is really the interdisciplinary research field between the AI, machine learning, computer vision, signal image processing, and also the biomedical applications, including the computational biomedical imaging, as well as the medical image analysis. So in general, my research in the past few years during my PhD, postdoc, and also in the future I want to pursue can be understood in this way to how can we use the AI to understand the human health in the different level. So to give some like general picture, so in the human level, for example, we can use the depth sensor in the hospital for like the more careful patient healthcare to help with our hospital laborers like the doctors and also nurses. And in the anatomy level, we can use the AI to illustrate the internal structures of the human body to understand the internal structures and also to do the analysis to extract the useful information from the images for the clinical deployment, including the diagnosis, the treatment. And furthermore, in the cellular level, we can also use the AI for the scientific discovery, for example, in the microscopy or the cryo-EM or cryo-ET images, where people are using this kind of the imaging tool to visualize the internal structures of the, for example, coronavirus and also the vaccine development. So this is very helpful, but we can see the different applications at the different levels where the AI can be helpful for the biomedical domain. And from the other orthogonal dimension, if we think about more from the engineering or the technical side, there are several things that I think will be very interesting. The first one is about the imaging, or how can we get the image, or obtain the data from the sensors or scanners. So this will be relevant to the inverse problems that we will introduce today. And after we get the images, after we get the biomedical data, how can we process the data to extract the useful information from that? This is also very important and relevant to the different downstream tasks. And after that, how can we translate and deploy this kind of technologies for the real world applications in healthcare, in the clinical application? So these are really the different areas or the fields of my research that I'm pretty interested in. And for today's talk, we will focus on this kind of anatomy level of the biomedical imaging, and with the specific techniques relevant to the generative diffusion models to solve the problems that is very interesting and also important. And this comes to the whole big picture of my research, just to introduce briefly about the high-level ideas that will be mainly relevant to the two parts. The first part is about the AI in the biomedical imaging. Under this topic, I'm very interested in the specific methodologies or technologies about the generative diffusion model, the implicit neural representation learning, and also the prior informed learning in general. And for the second part about the AI in biomedical data processing, I'm very interested about the multimodal learning, as we know that the medical data is inherently multimodality. So how can we combine the information there? And also self-supervised learning, how can we deal with like the data limitations or the bottlenecks from the biomedical applications? That's also a very important problem. And also in general, or maybe the final goal for this is a multimodal foundation model. So for example, if we imagine we could have some foundation model that can combine or fuse information from the complementary data sources of the different modalities and apply that for the different downstream tasks in an interactive way, in an explainable way. I think this will be very interesting what people term it as the generalized medical AI or GMAI, maybe something that we can achieve in the future. So this will be the big picture about the whole research field I want to share as a quick introduction. So if you are interested in any of this specific application topic or technical topic, feel free to reach out to me. I'm very happy to discuss further on that. And narrow down back to the topic in this talk, I will focus on the AI in biomedical imaging, and especially about the topic of the generative diffusion models. So back to the title of this talk, so solving inverse problem with the latent diffusion models through the hard data consistency. So I want to explain this kind of the most recent research work in these different fields. And finally, I hope this can also be something of your take-home message. You can answer this question. So firstly, why we care about the inverse problem in the biomedical imaging. Well, I'm not sure like how many people in the audience here is familiar about the biomedical imaging. Maybe some people working only with the lateral domain. So I want to briefly mention a little bit about the background. So why this is an important problem and what we care about in this setting. And the second thing, the diffusion model. So what is the diffusion model and why we want to use diffusion model to solve this problem? That will be the first question we want to answer. And why we want to use like the focus on the latent diffusion model, right? We have seen the diffusion models works well with the pixel space diffusion model and also the different algorithms. So why we want to use the latent diffusion model to solve this problem here. And finally, what is the hard data consistency? So this term is actually, which is also termed in our paper. We're trying to categorize the different previous work into the different categories. And also we call it as the hard data consistency to make it can be a reliable data consistency that works pretty well with the latent diffusion. So this will be the main outline for this talk. And I hope after this talk, you will also have the answer to this question. And also I will get back to this at the end to reinforce. Okay, let's get started. Yeah, sorry, I'm just a feel a little bit Yeah, so let's get started with the background. So what is the medical imaging and what kind of the inverse problem we are here? So firstly, for the X-ray or CT imagings, it's trying to reconstruct the cross-sectional images of the internal structures from the X-ray projections at a different angle. So for example, we will need to acquire thousands of the projections at a different angle to reconstruct some like artifact-free CT images in a computational way. But we also know that the CT scanning will expose the patient under the radiation or radiation. So how can we reduce the radiation exposure during the CT scanning? The sparse view CT reconstruction is one of the potential or possible answer for this, which means that if we reduce the required sampled projections from the different view angles, this could largely reduce the numbers of the projections we needed and also reduce the radiation exposure during the CT scanning. And also something we are also very commonly used is MRI, the magnetic resonance image, which is trying to reconstruct the cross-sectional slice or images of the internal structures from the measurements in the frequency space or the K space, as what people usually mentioned in the MRI domain. And if we could undersample the MRI, or if we could have like advanced MRI reconstruction algorithms that could reconstruct the artifact-free MRI images from the undersampled K-space data, that could also accelerate the MRI scanning, which are quite kind of slow for the current clinical protocol. So this is another motivation why we want to do this kind of undersampling for the MRI image reconstruction. So this is something that I adapted from the previous slides of the GF lecture. So there is some like short summary about the motivation, why we care about the sparse sampling medical imaging. So for example, for the CT, for the MRI, as we just mentioned. And there are more reasons. So, but in general, we can formulate this kind of problems from the different modalities as an inverse problem. So for example, here, we acquire the measurement data or the observation from the sensor domain. For example, the K-space for the MRI imaging or the radar space for the CT imaging. And in the fourth process, which is guided by the imaging systems, we acquire this kind of the measurement data from the image space to the sensor space. And in order to reconstruct or recover the internal structures of the human's body, we need to reconstruct the image from the measurements that is in the sensor space. So this process is called the sparse sampling medical image reconstruction, which can be formulated as inverse problems to reconstruct the information in the image space from the sensor domain. And if we are looking to the sparse sampling for the medical image reconstruction, then this inverse problem will also become ill-posed. So that's also the reason why we want to develop the different advanced algorithms to deal with this kind of the ill-posed inverse problems. And if we want to, if we formulate this a little bit more like into the into the mathematical formulation, so we always use the Y to denote the raw data that we acquired from the imaging systems. And what we want to reconstruct from the Y is the original image in the image space based on the measurements from the Y. So we will use this kind of notation across the whole talk we have here. And in the past 10, 20 years, there have been the generations of the different medical image reconstruction methodologies, from the statistical methods and also especially 20 years ago with the compressed sensing methods, where we introduced this kind of the sparsity regression in the optimization to solve the ill-posed problem. And more interestingly, through the data-driven methods, what we have overseen over the past 5-6 years. So this will also be the main focus for today's talk. So regarding for the sparse sampling image reconstruction, as we see like in the conventional methodology or in the current clinical protocol, for example, in the CT reconstruction as shown in the right figure, it always needs to acquire, for example, thousands or 2,000 of the projections at a different angle to reconstruct the artifact-free images for the CT imaging. And if we can do like the sparse view CT reconstruction, that could further reduce the projection or the angles that we need or required. So through this kind of the regularized reconstruction algorithms that we call, for example, the compressed sensing, We can add or we can introduce the sparsity in some transform domain as the regression in the optimization problem to solve this inverse problem in order to reduce the numbers of the projections we need to sample. So which means that we introduce some like the prior knowledge about the characteristics of the data or the properties of the data in order to reduce the measurements that we need to solve this problem. And with the introduction about the deep learning based reconstruction, this is also another different option or format that we could introduce the implicit prior through a data-driven way. So we hope that in this kind of the prior knowledge that can be nerded through a data-driven way, this can give us or push the limit of this kind of the sparsely sampling to another stage or another level that could further reduce the numbers of the projections that we will need to solve this problem. So this has been the very early stage and also the initial motivation for the deep learning based image reconstruction. So what we are doing here is that we want to nerd this implicit prior through a data-driven way that could reduce the numbers of the required samples that are needed to reconstruct the image. So at the very beginning, people are trying to use the neural network to train the neural network using the paired data of the measurement domain data and also the corresponding ground truth data in the image space to nerd this kind of mapping function to solve the inverse problem in this direction from the sensor domain to the image domain. And this actually has been begin this whole era what we call the deep learning based image reconstruction, which is trying to develop or use the neural network to know the mapping function through a supervised way that can nerd this kind of the transformation from the measurement domain to the image domain. So this comes to the very early stage of the research works, including the sparse sampling MR reconstruction, use this kind of the 3-layer neural network, and also the sparse view city reconstructions use the deeper network, while also based on this kind of supervised training from the paired data. But after that, there are a lot of following works, but at the same time, we also realize there may be something that we need to think deeper about the deep learning based image reconstruction. So in this paper published in the PNAS 2020, it reads about the question for the instability of the deep learning in the image reconstruction. So what exactly it is? It reads something about the reliability, the generalization, and also the data efficiency. We'll look into these three kind of the specific fields, specific questions in the detail. So for example, if we consider the reliability, when we're doing the reconstruction or other AI algorithms, we always want the model can capture some important details we are caring about in the medical applications. For example, this kind of the small structural changes, such as the tumor progression or shrinkage, which is pretty small structure anatomical changes, but that is very important regarding for the diagnostic issues or the treatment. But the AI model after the training can be insensitive to this kind of small structure changes. And how can we make this can be reliable using the AI for the real medical applications? And beyond this, we know that in the medical data, there have been a lot of heterogeneity, including the different modalities and the different organ, different contrast. So how can we make the AI model can be generalized to the different input data source or can be generalizable to this kind of different settings? So this is also something we need to care about when we use the AI-based model. And finally, we know that to train the AI model is always data hungry. But for the medical applications, the data collection and also annotation has always been very hard and also expensive. So this has always been a bottleneck for using or deploy the AI model in the medical applications. So how can we address this will also be a very important question. So in order to address these kind of challenges in the medical imaging, one of the solutions that I have been explored in my past research is to how can we propose or how can we develop more machine learning approaches or algorithms that can exploit the prior knowledge to address all these issues we're facing. This is what I termed as the prior-informed learning. And you can consider there could be different kinds of the prior knowledge that could be useful. For example, there have been like the population priors, which if you consider for the doctors, when the doctors have seen a population cohort of the different patients, there may be some like the prior knowledge or the experience that the doctors could be used for the new patients that will come to the hospital again. So it's the kind of the prior knowledge which is embedded from the patient population or like the distribution. And there are some other priors, for example, if the patient is under some like the treatment, for example, the cancer patient with the chemo or radiation treatment, always the patient will get this kind of longitudinal data from the time series data. How can we leverage all this kind of patient-specific information, which is embedded with the time series data, that can make the AI model you develop can be adapted or personalized to the specific patient? This is something we call the personalized prior, which is also very interesting. And finally, the phase priors, what we already know from the imaging system, from the microphysics background. So how can we incorporate all this knowledge with the learning-based model instead of only in the data-driven way? So I think these are all the things we can consider. There are a lot of like different priors we can consider, and also we think may be helpful for us to develop novel and also more efficient machine learning algorithms that can help us to better address these kind of challenges we have seen in the data-driven approach. And in today's talk, I will mainly focus on the first prior, what we call the population prior. So the question is that, how can we incorporate the population prior from the real data distribution? This comes to the first main topic about this talk, which is the generative model. So we propose to use the generative model to capture the data distribution priors that could further improve the deep learning model that we built to address these challenges, and also can tackle the inverse problems or the biomedical imaging that we are facing. So to give some like brief background about generative models, I may not be able to cover all the details here, but just want to give you some insight in the high level to say like, oh, what is the generative model? Sorry, diffusion model. It's trying to capture the data distribution in a generative way, like the GAN-based models that we have already seen. So there are two main paths or the process in the diffusion model. In the forward process, we add the noise gradually, step by step, to the clean image. And to get some like noise sample, finally belong to the prior distribution, which is the Gaussian or standard distribution. And in the reverse process, which is the generative process, we sample something from the normal distribution and then want to recover or reconstruct, or sorry, to resample the clean data from the underlying distributions that we want to capture through this kind of the model. So you can consider this as some way to get the mapping function or the transformation between the easy or the simple prior distribution, which is the standard normal distribution, and also the real data distribution, which is complicated and unknown. But we use this kind of the generative way to find a way that can capture the distribution priors into this kind of generative diffusion models. People have been applying this and propose it from the natural images, but definitely we can use that for the medical images. So if we are giving some like the cohort or the populations of the different patient data, for example, the lung CT images, we can also use the generative diffusion model to capture this kind of distribution of the lung CT images by doing this kind of transformation between the standard Gaussian distribution and also the real distributions of the lung CT images. So the key idea is to use the diffusion model, capture this population prior by modeling the data distribution. And there are different ways to understand the diffusion model, and maybe two main aspects. One is the diffusion probabilistic model, which we call the DDPM. The other is the score-based diffusion model, which is trying to describe the forward process and also reverse process as the SDE, the stochastic differential equation. This kind of the new two aspects are proposed in kind of independently, but actually they are correlated and also can be translated in each other through the different way. So I will not get into all this kind of fundamental details, but just want to give you some like high level insight. So by using the diffusion models, we can capture this kind of data distributions. And how can we do that? So there will be some like the neural network that we need to capture in the reverse process, which means that when we're doing the denoising from the noisy sample step by step, and we're doing the denoising to finally get the clean data can be generated. In this process, there is one called the score function, that is the gradient of the log likelihood of the real data distribution that can be captured and also parameterized by the neural network that we need to learn. So yeah, here we just assume that we have some like generative diffusion model that has been well trained that can capture data distribution. And with this kind of assumption, we can sample any sample from the Gaussian noise and to generate the sample from the real data distribution. This is what people have already been doing with the unconditional data generation. But we also find that generative diffusion models will be pretty suitable for the inverse problem solving. So why is that? As we mentioned earlier, we have this kind of the formulation with the measurements, which is given or observed as y. And with this kind of the known for the process, given x, we know how to acquire or obtain our measurement y. And in order to solve the inverse problem, as we mentioned earlier, we're actually trying to solve this kind of, or trying to compute this kind of posterior distribution, which is the px given y. So given the measurements y, what kind of the samples, what kind of the x that we could sample from this posterior distribution. And by using a very simple Bayes rules, we can get this kind of the derivation. And if we compute the posterior score distribution, which get the log and also the gradient on both sides, we can get this kind of the relationships. So what does that mean? The first term on the right hand is actually score function. So this is a score function that we use or that we trained in the unconditional diffusion models to get this kind of the distributions of the real data. And the second part is from our known for process. So with both of them, we can use this to compute the posterior score function that could be useful to help us to sample or to reconstruct the samples, or that could be consistent with the measurements given y. So this comes to the main ideas for using the diffusion models as a generative prior to solve the inverse problem. Just to give some like more formal measurement notations about this kind of for process. So here we kind of simplify this process as two main steps. So one is the phase-space transformation, and the other is the sparse sampling mask. So we think this is the for process that we have for both like either CT or MRI. And in this way, we can do the inverse problem solving use the generative model by firstly giving the trained diffusion models or score-based generative model, which is unconditional to capture the data distribution that is showing in the upper line, which is the px. And our final target is to get the posterior sampling or posterior distribution, which is the px given y. And in this way, the key idea is that how can we inject the measurement y into each of the steps to generate the samples from this kind of the posterior distribution that can be consistent with both the data distribution prior that is captured by the unconditional diffusion model, and also the observed measurements that is corresponding to the y. So in this like previous paper, we propose to do or solve this problem by inject the information of y into the each step of the diffusion model, and also to incorporate it into the images at each step. So specifically, we are solving this kind of optimization problems in each of the steps of the diffusion model or the generative model, where we have information which want to be closer to the current sampled image, which is the xt here. And also we want to be close to the manifold, which is the x given y, that is constrained by our measurements. And by solving this kind of the optimization objective, we can get this kind of the solution that can also be easily understand from kind of the physical or straightforward way. So for example, if we have some like the sampling mask, which is where we get our acquired measurements y, we just copy this kind of information, which we know is the correct, is ground truth, into the sampling step of each step. And for the information that we don't know about the ground truth, which is outside of the sampling mask, we combine the information from the from the current samples previously. And for this part, we just copy that from the current sample of the information. But for the other part, we have the sampling map. We combine the information from the measurements and also the current sample. So this can be some way can consider as a weighted combination from the two side information to get our sampled images through this kind of the generative process. And firstly, the unique advantage from the generative diffusion model is about the data efficiency. So you can see this is a totally unsupervised learning approaches, which means that during the training, what we only have is the clean image. And we use the diffusion model to capture the distributions of the clean image without any like the assumption about the measurements during the training, which means that we only train a single model which can be applied to the different sampling process or different inverse problems. And we also achieved like pretty good results compared to the previous baseline with the supervised learning model that I mentioned before. And this is another unique advantage we have seen by using the generative diffusion model as the prior, which can flexibly adapt to the different sampling process at the testing time using the same pre-trained model. So these are all the things that we have seen from the previous approach. But I also want to mention something, even though we have seen this kind of very exciting techniques or advantages from the diffusion model, but it's still something that cannot really apply for the real medical applications. So why? There are several like very critical questions we need to address. So firstly, to train this kind of diffusion model require the very large scale training data, which is hundreds and thousands of the training samples. But for the medical images in the real data, it's very hard to have this kind of samples from all different modalities or from all different cohorts or different disease. And the second thing is that in order to generate one samples for this kind of diffusion model process, it will need like hundreds or thousands of steps. So the inference time has always been a pretty critical point to reconstruct a single image that will need like 5 minutes, 10 minutes, or even longer time to get one image reconstructed. This is definitely what we don't want in the real practice. And finally, for all these kind of current approaches, we are all just focused on the 2D images. That may be okay for the natural image, but for the medical images, the real data is always like 3D or even higher dimensional 4D for the dynamic MRI or CT. So how can we make this kind of model can fit into the memory requirement to avoid this kind of the expensive cost to make it can be trained with the 3D or even 4D data? So these are always some challenges we're facing by using the generative diffusion models, although we have already seen like some unique advantages from this line of the research. So this comes to the very first motivation why I want to get into our this work is that how can we generate the diffusion model to the high dimensional and also high resolution medical images in the real world? So in order to do this, we need to propose and develop more advanced and also more efficient algorithms, including the data efficiency, the time efficiency, and the memory efficiency, as I just mentioned, to address all these kind of challenges we are facing for now. And for the current progress and also in these areas, so we have already seen like many existing works following in this line, trying to develop the different algorithms for solving the inverse problem using the generative diffusion models. But most of them are following or try to focus on this line to improve the model performance. So as shown in this kind of the dialogue, this kind of axis. So they are more trying to pursue like a better performance, a more reliable reconstruction by using the generative diffusion models. And for example, here are some like the several examples we summarized credit to one of the undergraduates in my lab who is working on this, to summarize this as like 2 main categories. So in order to solve these inverse problems, there are 2 main approaches in the line. So first one is what we call the soft data consistency or soft approach. So the main idea is that in order to add the data consistency from the Y, we are trying to compute the gradient-based update to update the data in each of the sampling step in the manifold of the XT. So this is what we call the soft data consistency, because you can understand that when we are computing this kind of gradient, and also trace back to update the manifold in the in the manifold of the T. That may not be exactly match what you should be in the manifold of the exterior, which is the clean data, which can be corresponding to the measurements Y. And in the other line of the approach, what we call the hard approach or hard data consistency is that we exactly, extremely, or strictly want to have this kind of the data consistency, which can be satisfied in the clean data that is corresponding to our measurement Y. And this is, you can do the projection on the manifold of the clean data. You can do the optimization on this manifold. And this is one line of the research following this line and trying to do the hard data consistency. And beyond this all these kind of algorithms trying to pursue the better model performance, there are also some works that are trying to address the efficiency issues, as we can see, especially for the medical applications. So the most interesting, just to name a few, some interesting example is to use the 2D diffusion models for solving the 3D imaging problems. So as you can see here, you can just regard each slice of the 3D image as one of the 2D image, right? And then you train the 2D diffusion model from your pre-trained model, and then you're trying to generate the 3D images slice by slice using the generation of every slice of the images with your pre-trained diffusion model as a prior with your measurements. And in this paper, which just published in the ICCV 2023, they're trying to do this kind of the reconstruction through an alternative way, which means that they have the slices in the different orientation. And you can consider this kind of reconstruction. It may work, but they also have some constraints. For example, they always include the regularization to constrain the smoothness across the different slices. And you also have the compromise of the model performance since you are doing the reconstruction slice by slice. And also because you are doing the reconstruction slice by slice, so it will largely increase the inference time that you are using. To generate a single slice of the 2D image is already pretty time consuming. To generate the whole 3D image slice by slice, you can consider how expensive it can be regarding the time assumption. So these are interesting recent works that we have already seen in these areas. So what we can do to achieve the other dimension, which means that we want to have both the better model efficiency, but also to maintain the good model performance. So this is the areas we want to tackle on as the motivation for our work. Our proposal here is that we want to use the latent diffusion model as one of the potential solutions for this. Why this can be helpful? So firstly, for the latent diffusion model, we're trying to encode the data from the image space into the high dimensional data space to the lower dimensional embedded space. And in this way, all the diffusion model training, processing, inference will happen in the lower dimension. That will give us a better memory efficiency, time efficiency, as what we can see in the stable diffusion. And the other thing is that because of this kind of the latent code diffusion model, we find it pretty more generalizable by generalize the latent diffusion model into the other domain, for example, from the natural domain to the image to the medical image domain. So this comes to one of the potential or our hope to say like, oh, if we could do all the things in the latent diffusion, maybe we could make this can be feasible for the high dimensional data, including 3D and also 4D. But the other key challenge question is that how can we guarantee the data consistency in this case with the latent diffusion model? So this really comes to the key question, research question we want to tackle in this work. So in this research work, which just put on the archive over the summer, is that we propose this kind of new methodology to solve the inverse problem with the latent diffusion model. And especially, how can we constrain or make the reliable data consistency in this process? So you can consider, firstly, why this problem will be difficult and challenging. It's because the nonlinearity from the encoder-decoder you have seen here on the left figure. So because of the nonlinearity, so no matter if your inverse problem is linear or nonlinear, it will essentially become a nonlinear problem with this kind of encoder-decoder. So how can we make this kind of the data consistency really injected in the latent space and also guarantee the good data consistency in the generation or the reconstruction? So in order to do this, we are doing this kind of the main 3 steps. I will describe step by step. So firstly, if you consider in one of the sampling steps in the latent diffusion models, we want to do the consistency with the measurements Y. So we want to firstly get this kind of data back to the clean data manifold, which is the Z0 here. The Z means the latent code. And in this way, we use the Tradice formula that has been used commonly in the previous work, like the DDIM or the DSP model, to predict the clean data from the current time steps T. And after this, we're trying to do the data consistency. So in order to do this, we choose to do a car data consistency through an optimization problem. So what we're doing is that we are trying to optimize or to update the predicted latent code in the clean latent space, which is the Z0, by including the information from the measurements Y. And in order to do this, we're actually solving this kind of the optimization problems. And here there are some like the maybe the training strategies or optimization we're using to speed up this kind of optimization process is to use the predicted Z0 from the previous latent code ZT as a unitization to continue to do the optimization based on the constraint of the Y. So this process is to make sure that, okay, for now, in the clean latent manifold, we are make sure the current data sample, I mean the Z0, is consistent with our measurements Y. And after this is just one sampling step. We need to go back to the sampling process and continue this kind of sampling procedure with the latent diffusion model. So we will need to go back to the manifold of the ZT again. So in this way, this comes to one of the critical problems. So what we're doing here is the new approach we proposed called the stochastic resampling. So which means that in order to only get the predicted or get the manifold of the ZT from the Z0 after the optimization, we also include the information for the previous random sampled ZT from the last cycle, from the current cycle before the optimization. And the reason for using this kind of approach is to reduce the variance when we predict the ZT back to the manifold of the time T. So here in the paper, we have like this kind of 2 proposition. The first one, the stochastic encoding. This is what people are usually doing, which means that they are trying to have this kind of the connection. So based on this kind of the connection from the DDPM or the diffusion model, we could have the relationships to say like how can we predict the any sample at the time manifold T from the clean data Z0. So in this way, it should it could give us something, but it has a pretty high variance in this kind of the remapping process. And in this paper, we propose what we call the stochastic resampling, which is also include the information from the ZT prime, which is the unsampling data sample before the optimization, to construct the information from both sides to construct this kind of the new manifold, or to update this kind of the new sample in the manifold of the T. So there have been quite a lot like the theoretical analysis in our paper to say like why this should give us a lower variance, and also why this should work, and also in different ways. So in this paper, we also will do some like quick update in the next few days about the new version. So feel free to check that. So get to the summary. So here is the whole resampling algorithms we are proposing here. So all the previous approaches is like the encoding process, and also the Tradice formula we use to predict the Z0 in each of the unconditional sampling step. And the key part is here, how can we inject this kind of the hard data consistency through the optimization with the measurements in the clean latent manifold. And also more importantly, how can we map back from the Z0 to the ZT to get a low variance into this kind of manifold of the ZT to continue the next step of the sampling process. So this kind of the procedure is what we call the hard data consistency in our paper. And we are not doing this for every of the sampling step, because as I just mentioned, usually we'll have like hundreds of thousands of the sampling steps in the diffusion model. But we find that we just need to do this kind of the hard data consistency in some of the sampling steps across the whole sampling procedure. And it can already give us a good guarantee about the data consistency with the measurements. And also more interesting is that, as shown in some other paper, we find there are 3 stages or 3 intervals in the whole generation process of the diffusion model. The first one is most likely in the noisy data. The second one is some like data with both the high frequency noise and also the low frequency details. And the last part is most about like clean data. We find that if we only do this kind of the hard data consistency constraint in the latter 2 stages, that can already give us a pretty good guarantee about the data consistency with the measurements Y through this kind of process. And there is some like the results we're showing, for example, in the medical images. So one thing that I really want to note here is here, in order to get the latent diffusion models for the CT images, we are not training from scratch. We're actually fine-tune the stable diffusion models from the lateral images. And by using only 2,000 CT images, it can give us a pretty good sampling generation qualities of the model. And also we use that as the generating priors to solve the inverse problems. And here we achieve the state of the art for using the diffusion model in the sparse view CT reconstructions. And by compare with the previous approaches, which is on the pixel-based diffusion model, as well as the latent DPS. So actually the latent DPS is not what has been published in previous paper. Is some of the application studies we mentioned here, because prior to our paper, there hasn't been any paper working on to have this kind of algorithms can solve the latent diffusion models with the inverse problem solving. So the latent DPS is that we apply the DPS algorithms, which was originally designed on the pixel space to solve the latent diffusion models in these inverse problems. And we see that our approach can achieve the state of art compared to all these kind of the baselines, either in the pixel space or in the latent space. And this kind of methodology is not only useful for the medical images, and definitely useful for like the natural images. We tested on like the different tasks of the inverse problem, including the inpainting, the deep blurring, the superior solution, and also the different data sets for the natural image benchmarks following all the other baseline papers they are doing. And especially you compare with the latent DPS, which is working in the latent diffusion model, and also the ReSample, our algorithms, we can really see like how this kind of the fine detail can be captured by enhance this kind of the hard data consistency using our algorithms. So there is some like the more quantitative matrix we're comparing with all the baselines, and also achieve pretty good results in all these kind of different tasks and also different data sets. So this comes to something we can fill into the current diagram for now. So we think our algorithms, ReSample, can guarantee the data consistency with the latent diffusion models, while also maintain very good the model performance in this when using the latent diffusion model. And again, back to the diagram we have seen over the existing works, we think the ReSample can be filled into this line of the hard approach or hard data consistency. While the different things is that all the previous approaches are working only with the pixel diffusion models. Well, we are exactly the first few works that are working with the latent diffusion models. And because we have this kind of resampling algorithms that can guarantee the data consistency with the latent diffusion models. So for now, you can consider this really opened the door to a lot of different opportunities, especially for the high dimensional and also high resolution medical images in the real world. So for example, in this kind of application case, we train the latent diffusion model firstly to generate the 3D knee MRI images. So this is really the 3D medical images, not the 2D images, not only the 2.5D images. And here we show the cross-sectional slices that is generated using the latent diffusion model. And can you distinguish like which one is the generated and which one is the real data? Yeah, if I remember correctly, I should put the real data as the right one. Yeah, but you can see like it's pretty good quality, but this is only for the generation. And for the next step is that with the resample, with this kind of generation model of the 3D data from the diffusion, from the latent diffusion, we can guarantee or we can have the data consistency to make this kind of can be, for example, the 3D reconstruction or other inverse problems into the latent diffusion. And there is some other examples we're doing with ongoing research works for the dynamic MRI images. So this is some like the video diffusion models we're training to predict the dynamic cardiac MRI images. For example, we are giving the first 5 frames in this model and trying to predict the other frames, giving the conditional frames, and in this kind of the autoregressive way, we can get the whole videos for the cardiac images, even though only the first frames are given at the ground truth. So this kind of like get back to the conclusion and also the end of this talk. So we discussed many about these papers, about how we solve the inverse problem using the latent diffusion model and what kind of the approaches were proposed here, which is we termed as the hard data consistency. So we firstly mentioned something about the inverse problem in biomedical imaging as a brief background. So why we care about this kind of problem, we care about like the safer CT scanning, we want to have a faster MRI scanning. And when we want to use diffusion models, we also see like how the diffusion models can help us to capture the data distribution prior, and also the unique advantage compared to the previous deep learning-based image algorithms. For example, the data efficiency with unpredictable training, the flexible adaptation to the different sampling procedure. And why we want to use the latent diffusion model? Because the diffusion model is pretty expensive in the time assumption, the memory cost, and we want to have a better model efficiency by using the latent diffusion model to further improve the model efficiency in this algorithm. And finally, we show that our algorithms, which is called the ReSample, use this kind of the hard data consistency by doing the optimization on the clean data manifold, or exactly the clean latent code manifold, to guarantee the data consistency. So this comes to the end of this talk, where we specifically talk about the specific topic under the AI in medical imaging, and especially with the relevant techniques, which is about the generative diffusion models. And finally, I want to get back to this kind of high-level picture. I really believe the biomedical AI can really help people to understand the human health in the different levels. And I look forward to share the other parts of my research with the department and with you. And feel free to reach out to me if you have any interest and also want to discuss more. And finally, I want to acknowledge and thank you for all the students I'm working in the biomedical AI lab, and also all the collaborators in the X, in the BME, and also medical school, and especially the co-authors of the latent diffusion resample paper, Bowen Soming and also Professor Chu Qin, and also the other 2 students working with me, working on the dynamic MRI prediction, and also the consistency model with the continuity to further improve the time efficiency for the diffusion models. Yeah, so this will be the reference that I listed in that diagram. So please feel free to check out about all this kind of very cutting edge and interesting research works that including both the soft approaches and also the hard approaches. Yeah, so this will come to the end of my talk. Thank you so much for your time and attention. I will take into
Yeah, I have a question which is a bit off the topic. So like from like an estimation theory point of view, ultimately you get a sample where you can draw a sample from a stereo distribution of x given y. So like, like you So like during testing, do you like draw one sample or like take sample averages and estimate of all that and then see?
Yeah, that's a very good question. Yeah, I remember Jeff asked the same question when I interviewed here last year. Yeah, so I can tell you in our the first work that I just mentioned for the score SDE. So we're actually just randomly sample some like noise and to generate a random sample. So definitely you're right. So what we finally get is the distribution instead of some like deterministic image. So if we are thinking about the previous deep learning based reconstruction, if you input some measurements, you can always get some output. You don't know how accurate it is. You just get something right deterministic. But this is not different. This is different. So in all this kind of the paper reported of the numbers, I think they just sample something with the random noise and to get their scores or the matrix reported as in the paper. But there are also a line of the papers with the diffusion models about the uncertainty estimation or quantification. So in one way, you can say like here, because we obtain is a posterior distribution, so that really give us the chance to understand from the model that which part is have a larger variance where the model is more confident about a prediction, which part may need like more constraints on. So this also opens the door for this kind of uncertainty estimations in this line by using the posterior distributions along this line. But that's also some questions definitely we need to address. And actually, there are also some works collaborating with like Professor Chichin's lab. Here is some like ongoing project trying to investigate the mapping function between the noise and also the real data, where we find like actually if we train different diffusion models, if you input the same random Gaussian noise, you actually will get pretty similar results from the different diffusion models. Yeah, which we call like the model reproducibility. So that's also very interesting work. And it not only happened for the unconditional sample, it happened for the conditional sampling and also this kind of the constraint sampling with the diffusion model with the measurements constraint from the Y. So definitely there are a lot of things that still need further investigation and we're still not knowing very clearly. But I think this is also very interesting research questions that will can be investigated more.
How do you do that? In the SDM, it takes like millions of interviews. Like you can do it for easier. It is really something. Yeah, there are existing works at like part of this, but the works have not reported results on our scale. I just wonder if you have any experience with SDM. Yeah, I think actually, the diffusion model is quite given active that if it's correct. So not superior, it's likely.
Yeah, that's true.
Correct. I guess like from like compressed sensing perspective, probably like above a certain threshold, like you get a deterministic result pretty much.
Yeah, exactly. That's true. Yeah, definitely. I mean, so this is something that we are facing pretty new with this kind of approaches, either from like deep learning based reconstruction or computer sensing. We should get some like deterministic results as something. So, but essentially we know it should have like multiple solutions or multiple answers that can be corresponding to the same measurements if it is opposed, right?
I mean, I guess Alex Marquez said a bunch of like compressed sensing theory like stuff.
Yeah.
It's not like diffusion models, but they are trying to get to the point of like maybe there's a phase transition or whatever if they have enough samples and you get a deterministic, just like sparse solution kind of thing. Yeah,
that's true. That's definitely correct. So in that ongoing work, we also find some similar phenomena. So if you are using the diffusion model to train on some, for example, the small set of the data samples, at the very beginning of the training, it just memorized the data samples. So it memorized this kind of the mapping from your training data to the noise image. So in this kind of stage, it does not have the generation ability. it just memorize all the training data you have already seen. And after training for some time, it can have both the generation ability, but also we can still select this kind of reproducibility phenomenon in the model. So I think, yeah, definitely there should be some like more theoretical things we should investigate it, like in the computer sensing, yeah, about this.
Another thing I want to ask is like, so latent diffusion helps with the computation, right?
Yeah.
So there's also distillation approaches.
Yeah, right.
So then, like, which one is kind of the better?
Yeah, that's a very good question. Yeah, we're actually looking into that. So in one of the ongoing work with another undergraduate, we are trying to use the consistency model to further improve the time efficiency, like you mentioned. So previously, we thought ReSample algorithms is a very good fit for the consistency model, because in each of the steps, we need to go back to the X0 and we add the data consistency constraint, and then we go back to the ZT, right? So we think that, okay, consistency model can do this kind of one-step generation from any time step to the clean image. So we just want to incorporate that as the generative prior instead of the diffusion model, to say that if we can do like the one-step or two-step sampling or inverse problem solving. But finally, we find that this is not that kind of easy. You can, by using the consistent model, which is also somehow the distillation from the EDM model, right? So even though you can get a very good quality from the image in every step, but it's not that kind of easy to constrain or to add the constraint or information from the measurements into your sample step. So we're trying for like 30 steps or 40 steps. It does not give us the results as good as all this kind of the current diffusion model-based algorithms we have already seen. So I agree with you. We can also do like the progressive like distillation on some like existing diffusion models and to reduce the number of the sampling steps for that. I'm not sure if that could work. That may be something that could be tried. And for now, we're doing is by doing something more through like the shorting bridge or the control node. So we want to use this as a conditional information to control the pre-trained diffusion model by adding some like the additional module part to add the conditional information, while also add the data consistency to guarantee this kind of reliability of the generation images. So it's still ongoing. I'm not sure if that could work, but I will keep you updated. Yeah.
So yeah. I saw some results comparing with diffusion posterior sampling paper, and I know that they operate in the image space.
Yeah.
But I mean, if I'm not mistaken, like when they do the data consistency, they do it in a they don't solve an optimization.
Yeah,
Just to take the gradients only once.
Exactly.
So and there.
Every step, right?
In every step.
Right.
What I saw here is that you're solving an optimization problem at every step. I know it's in the latent space. It's less computation. So I was just wondering how much like the using like the latent space versus the image space, and using multiple optimization here versus only one like gradient step in the image space.
Yeah, that's a very good question. So firstly, by using the latent diffusion model, is that we want to make this kind of open the doors for the high dimensional or high resolution images. If we only keep with the pixel diffusion, then the memory will always be an issue, right? And the second thing, about this kind of optimization. So the optimization is not done in our algorithm for each sampling step. So we're do this for every like 10 sampling step or some sampling step. So this could be some hyperparameter. You can get a trade-off between your sampling or reconstruction quality and also the time cost. And you are right. So in each of them, there will be like multiple steps to get the optimization, because this is an optimization problem. But we are trying to say like, okay, in this kind of the trade-off, we can both get the reliable reconstruction algorithms, but also can make this kind of into the latent space. Yeah, we also do have the comparison between the DPS and also the our algorithms. So from the 2D images, I would say for both the memory and also the time efficiency, there is not large difference in the latent or the pixel. But we want to make this can be something that open the door for like the 3D images, like what's it ongoing, to really make this can happen, to get the 3D reconstruction, for example. Yeah, so that is our motivation here. Yeah, thank you.
I want to follow up on Ismail's question. So
this to me, the hardest step is the one he was just asking about, right?
Yeah.
This, the hard consistencies constraint. So the word hard has two meanings here, right? It's challenging. Yeah. So, and I actually was following along in your paper. In the paper, you had a ticking off.
Oh, yeah.
I see that's disappeared, but you're focusing now on the initialization. So I'm just curious, how many iterations have you, because even though it's in the latent space, you have to generate the 3D volume, run it through your forward model, right? That's not cheap, right? And do back propagation through all that, right? Right. Well, you have to do the gradients of all
it's on the like,
gradient.
Yeah, exactly.
So how many iterations do you find are needed to really do that hard constraint?
That's a very good question. So firstly, I need to claim here that we have this kind of updated version of the algorithms, which we think will be more elegant and also clear. By removing some modules, we think will be not be that kind of important, but introduce more hyperparameter. So just to get rid of that. We haven't updated this on the archive. Yeah, sorry for this kind of confusion. Yeah, and for like the details about the optimization steps, yeah, I think maybe Bowen can give some detailed answers about this.
We have
300 inner iterations for the optimization problem?
Exactly. Oh, wow. And however, the iteration is much faster than DT iteration because the encoder is quite lightweight.
Oh, okay.
Yeah.
I see. Okay.
So on the clean back.
Yes.
Yeah, and we find like by using the DPS in the diffusion, which is what we call the latent DPS, the key issue is that when you calculate the gradient through the A and also the decoder especially, then the gradient will not be that kind of reliable. And in this way, in this paper, we also find like the state size of the gradient is pretty sensitive in order to get the good results. So in this kind of nonlinearity decoder case, it's very hard to have, I think, Bowen, they also tuned a lot in their state size to get the reliable and stable results. So we think this kind of the optimization, the clean manifold will be a more stable things that could help with the consistency and we get that. Yeah, but definitely this is something like you will look like will be pretty consuming and stable. Yeah.
I mean, it's kind of
for
like,
the optimization.
Alec Marcus used the GAN there, right? He had a similar optimization. His whole reconstruction problem.
The glue loss, something like a glue loss.
Something like that.
Exactly. So because they have this kind of gradient through the decoder or encoder, so they also have the similar problem issue with the latent DPS actually. Yeah, with the state size.
It's up to you, but you have questions in chat. It looks like.
I see. Yeah, thank you. So the reminder. Okay. Yeah, thanks. Multimodal foundation model, biomedical domain, one unique challenge. What could be interesting research direction? Wow, that's cool. Yeah, I didn't cover that in the talk, but I'm really happy to briefly say something in the high level. So for the multimodal foundation model, so I think there are two key points. Regarding for the technology, one is the self-supervised learning, right? So how can we learn the good representation or features from the multimodalities? And the second thing is about the multimodal. So how can we combine the information from the different modalities? And also if there are like complementary information or how we can use that for the downstream task for the outcome prediction or something. So I think these are the two key parts regarding for the multimodal foundation model. I mean, the self-supervised learning and also multimodal learning. But regarding for the real applications and also what's going on in the project done by the students in my lab, I feel like for the biomedical domain, actually one thing very difficult is the data availability. Yeah, so previously we mostly doing something about the image and the text, for example, the X-ray images and also radiology reports. That is what we have the available public data set. And for now, we are trying to go beyond this two modality, for example, to the genetics, or the EHR, the health records, or some other modality. But we find that if we want to get this kind of the available data access, that is already something pretty important, pretty hard. But we are in the progress of that by within the support from the Precision Health Program of the Michigan. They have this kind of the very good data source from the Michigan Hospital with the EHR, with the genomics, and also the images. So it's ongoing, but I think that is something pretty, critical challenge for the multimodal foundation model. And the second thing is about the technology, as I just mentioned. How can we efficiently fuse the information from the different modalities? And also if they are, if it should be like fused, for example, for some disease, this may be determined by the genetics and also the image together. For some like disease, this may just depend on the genetics for 70 or 80% probability. So I think all these kind of things will be the key questions we need to explore in the multimodal foundation model. But I'm pretty excited about these areas. And also corresponding with the large language model, we have already seen some like this thing works in this line. So I'm happy to chat more about that if you can, if you want to talk. Why do we want to treat latent diffusion model differently from because the nonlinear DPS perform well? Yeah, that's a very good question. So because the DPS can solve both the linear and the nonlinear problem, then that is why we use the latent DPS as one of the baseline here. So definitely you can consider it as a nonlinear problem and use the DPS to solve that. And we find it's not that kind of easy to say you can really get a very good data consistency by using the latent DPS. So that's also one of the reasons we want to propose this kind of hard data consistency instead of only the gradient space. And add a downsample matrix before the system. I'm not very well understand this question. Yeah.
I can you hear me?
Yeah, I can hear you.
I just mentioned if you downsample or upsample, you don't need to train a encoder or decoder. Right.
Yeah, that's a good one. So actually, the encoder decoder in the stable diffusion is doing something similar with the compression instead of only like the semantic encoding. Yeah, so yeah, the key idea is there. So we want to decrease the dimensionalities that where we train or use the diffusion model for the generation, and also to make this can be like memory or efficient feasible. Okay, thank you so much for all the questions. Yeah. Any other questions? Yeah, if there is any questions or if you are interested about the research topic that I mentioned, feel free to come to my office hour, which will be the 1:30 p.m. to the 3 p.m. every Thursday. I'm very happy to talk about your ongoing project or any research idea you may have that is relevant. So thank you so much.